significant, and the estimate is significant. However, we find that this ACF plot, I mean, let's start with like the standardized residuals. The standard residuals are not bad, I think. The ACF plot, the first leg of this ACF plot is outside this confidence interval, but I mean, it is only like outside this confidence interval by a very little amount. So that is acceptable. The QQ plot is good. The thing that is not that good is this LB statistic. So you can see that the p-value of all the legs of the LB statistics are less than 0.05. So this suggests that our model is actually not a very good model. We still have some correlations among the legs. I mean, we still have some correlations in the residuals. Okay, so that is, it is not a very good model. Okay, so from here we can see that everything except LB statistic. Okay, and let's also record AIC and BIC here. So AIC here is 1.40 and BIC is 1.42. Okay. Okay, so that's our model number 1. And we'll do the same thing on our model number 2, which is this AR5 model. So run code, and this is what we got. Okay, so we first notice that all the coefficients are statistically significant, so which is good. And there's no parameter redundancy problem here because it's just a AR5 model. Okay, so the next thing that we want to check is whether this is a causal and invertible model. So that's what we check here. Okay, yeah, so you can see that if we like rewrite this ARMA model to a MA model, then the coefficient converges to 0. Okay. And if we want to rewrite it in an AR infinitive form, again, you can see that it converges to 0 very quickly. Okay, so this suggests that our model is a causal and invertible ARMA model, so which is good. Okay, so we checked the parameter redundancy, we checked the causal and invertible. Both of them are good. And then let's move to the residual plots. So again, the standard residual plots, I think it's good. The ACF plot, I think it's better than the ACF plot for the MA1 model because all the legs here are within this confidence interval. The QQ plot is good. And the problem again here is LB statistic. So again, all the p-values of the LB statistics are less than 0.05. So they suggest that our model is not a good model. We might look for some other good model. We might look for better models. Okay, so here we're basically the same conclusion as our MA1 model. So everything except the LB statistics are good. And let me document the AIC and the BIC here for future comparisons. So the AIC here is 1.42 and BIC here is 1.47. Okay, so again, clearly this AIC and the BIC are larger than the AIC and the BIC for the MA1 model. So that suggests the MA1 model in terms of the information criteria, the MA1 model is better. Okay, but anyway, as I said, both of these models suffers from these LB statistic problems. So all the LB statistics are statistically significant. So suggesting that so this model is not that attractive. Okay, so then what should we do? So a couple of things that we can try here. So like remember that our goal is try to fix this LB statistic problem, right? So a couple of things that we can try here. So just by looking at the ACF and the PSF plot here, you can see that how about that we increase the order of the AR1 model. So for example, here you can see that maybe this is an AR7 model. But this is not a very, very good like direction. The reason is that like the AR5 already has a very large order. So you basically have 5 like basically like the independent variables to explain your time series. But now you want to include to 7. Okay, so that's not very attractive. Remember, like our goal is to find the simplest model. But now it seems you are trying to make our model more complicated. But you can definitely try that direction to increase the order here. And another way that you can try is to combine this AR and MA model together. And that's what I do. Okay, so this is what I do. So instead of trying to increase the order of the AR or MA model, I combine this model, 2 models together. And I just estimate this ARMA51 model. Okay, so this is ARMA51 model. And let's run this and see what we can get. Okay. All right, so a couple of observations here. So first you can see, unfortunately, all this coefficient become statistically insignificant. So AR2 to AR5, all the p-values are greater than 5%. Okay, and even like 10%. So this suggests that AR2 to AR5 are perhaps not good like explanatory variables for our time series. Okay, so we will keep this in mind. Okay. All right, and then we want to see if our problems, if our model suffers from the parameter redundancy problem. So I run this code. So to check basically to check if there, if it does have some similar roots. Okay, so that's what I got. Okay, so that's the polyroot of the AR part, and that's the polyroot of the MA part. Yeah, and I checked it, and I don't think there are any roots that are very close to each other. So that suggests there is no parameter redundancy problem in this ARMA51 model. Okay, and the next thing is that I want to check if this is a valid ARMA model. So I do these 2 checks. So you can see all the coefficients converge very quickly to 0 if you want to write this ARMA model to a MA infinity representation or a AR infinity representation. Okay, so everything converges to, all the coefficients converge to 0. I mean, like maybe this part not converge to 0 very quickly, but I mean for the MA part, sure, it converges to 0 very quickly. Okay, here you can still see the pattern, even though it does not converge very quickly, but eventually it will converge to 0. Okay, so that suggests our model is a valid ARMA model. Okay, then the next thing is to check the residues. Okay, so the residues from here, you can see the standardized residues, ACF plot, normal QQ plot are all very good. The only thing, and more importantly, the LB statistics becomes very good. So all these lags, the LB statistics for all those lags becomes statistically insignificant. So that means we will not reject our model, and we will think of our model as a very good model. Okay, so from all this analysis, you can see that we got everything except coefficients. Okay, so we got everything except the coefficients of AR2 to AR5. Okay, the significance. Significance. Okay. All right, and I will also write down the AIC and the BIC here. So AIC here is 1.38 and BIC here is 1.44. Okay. So compare the AIC and the BIC to our MA1 model. You can see that the AIC becomes better. BIC is becomes large. Okay, and compared to the AR1 model, both AIC and the BIC in this ARMA 5.1 model are better. Okay, yeah, but again, what the model shows here is that it still has some problem. The problem comes from the significance of the coefficients of the AR2 to AR5 terms. Okay, so the next natural step to address this is to throw away the AR2 to AR5. Okay, so this is like the technique that you will use for the cross-sectional data, right? So remember, in the cross-sectional data analysis, and if you find that any of your explanatory variables are insignificant, the way that you address that is to throw away that insignificant variables and rerun though and see if the model becomes better. Okay, so so we use the idea here. Okay, and that's what I do. So I throw away AR2 to AR5, and I just estimate a ARMA 1.1 model. Okay, so that is this model. So that is a ARIMA 1.1 model. So because this the middle one stands for the difference. Okay, because we want to do the first difference. Okay, so now let's run this model and see what we got. Okay, so first you can see we got all this like the p-values for the AR1 and the MA coefficient are statistically significant, which is very good. Okay, and I also checked this parameter redundancy problem very easily. You can see that there does not exist any parameter redundancy problems. And I also check if this is a valid ARMA model, and sure it is. The coefficient converges to 0. Okay, and now let's move to the residual plots. So you can very easily see that all the residual plots are perfect, I should say. Like even for this QQ plot, like I only see like these 2 points might be a little bit off, but everything else are very, very good. The standard residues, standardized residues, yeah, I think it's good, not that bad. The ACF plot, very good. The LB statistics, very good. Okay, so you can see that after we do all these checks, it seems that this model satisfies all the criteria that we need. Okay, so this model is that everything is good. Okay, and finally, let's check the AIC and the BIC for this model. So the AIC for this model is 1.737, and the BIC for this model is 1.40. Oh, this is maybe 1.38. Okay, so compare this AIC and the BIC values with all this AIC and the BIC from previous models, that we can see that our AIC and the BIC are the smallest. The AIC and the BIC for this model is the smallest. Okay. Yeah, so very good. So it looks like every criteria, the significance, invertibility, parameter redundancy, residues, everything for this model is good. And moreover, it has the smallest AIC and the BIC among all the models we have considered. Okay. Yeah, and finally, to check that this is your best model, or this is a model that you want to use, we can increase the order of the ARMA term a little bit. Okay, so for example, here, let's increase the AR part, the AR order a little bit. So let's check this AR ARIMA 2.1.1 model. Okay, so let's check this ARIMA 2.1.1 model. So again, you can see that the AR2 coefficients becomes insignificant. Okay, the residual plots are good, and yeah. So and also this BIC increases a little bit. The AIC I think is also larger because this is 1.377, and what we have in our early model is 1.375. Okay, yeah, but the most important thing here is that this AR2 coefficient is statistically significant. Okay, And this suggests that this model, this ARIMA 211 model, is worse than this ARIMA 111 model. Yeah, very obviously. And finally, I check this ARIMA 112 model. So I increase the order of the MA parts and of the order of the MA like by 1, and this is what I got. Okay, so you can again see that this coefficient of this MA2 is statistically insignificant. And this AR1, it is like just like marginally significant. Okay, so if you choose a p-value at 1%, you will accept this model. You will not reject it. It's insignificantly different from 0, right? If you like change the p-value to 1%. Okay, and moreover, you can check the AIC and this BIC. Both of them are larger than the ARIMA 111 model. Okay, yeah. So this again tells us that this ARIMA 112 model is not as good as the ARIMA 111 model. 112 model is not as good as the ARIMA 111 model. Okay, so both of these models are worse than ARIMA 111. Okay, so to conclude, we'll use ARIMA 111 to study WRF. Okay, right. So any questions here? I think it's straightforward. It uses some techniques here, but I mean, I think you guys should should be very comfortable with all these techniques, right? So we start with some like candidates of the ARIMA models just by looking at the ACF and the PACF plot, and we use that as our starting point and try to find our best model. Okay, and the result here is very, very obvious, right? This ARIMA 111 is strictly better than all the other models. Okay. Okay. Yeah, so that's the second example I think I want to go over for this ARIMA example. Okay. Yeah, so I think at this point you should be very, very comfortable with all this analysis. Okay, and now I think I want to go over an example in this BK textbook, which I think is interesting because it uses some techniques that we haven't discussed yet. Okay, so the data for this example is this temperature readings data. So we discuss this data as our introduction, and we see that the ACF plot of this of this temperature reading is not good. It does not die out very quickly. So what we do is that we take the first difference, okay, and this is what we got after we take the first difference. Yeah, and the textbook said that it will just use the first difference to proceed. Okay, so yeah, so that's what's the ACF and the PACF plot of the first difference of the model of the time series. Okay, so you will see that I think this is very clear here because the ACF plots, certainly it is like tails off, like has this like sine and cosine patterns, and this PACF plot just cuts off at leg number 1. Okay, so I think this, yeah, I think this is a very clear picture, clearer than the examples that I gave, right? The examples I gave, I think it's a little bit hard to tell if you want to choose a AR1 or, I'm sorry, if you want to take a AR5 or MA1 or ARMA 5.1. But here I think it's very clear. Okay, so the textbook says that it seems that this AR1 model is the appropriate model for this time series. So it just fits this ARIMA 110 model, and that's what it got. Okay, so the coefficient of this AR1 is 0.8239, it is statistically significant. And you can easily check that since this coefficient is strictly less than 1, so this is a stationary model. It is causal and invertible. And of course, since that we only have this AR part, so there's no parameter redundancy problem here, okay? All right, then the textbook checks the residual plots, okay, and it is what it got. So this is the left-hand side is the ACF, and this right-hand side is the PACF. So clearly, there's no autocorrelation left in the residuals just by looking at the ACF and the PACF plots. Okay, so everything up here is what we discussed. So this textbook also discusses the LBP test. So I think it's just the LB test we have in our R code. And this is what it got. So you can see all the p-values are larger than 5%. So again, there's no evidence that there's any correlation left in the residuals. Okay. Yeah, so up to this point, this is like everything we have seen in our example. And it does some further checks of the residuals. So it checks this QQ plot. So this first plot is the QQ plot, and it also like plots the histogram and also like the residuals versus the fitted values. But we can just look at this normal QQ plots. Okay, so you can see that there are some outliers actually in this plot, especially I think this observation number 58. Yeah, I think I'm pretty sure that this observation number 58 would be outside the confidence interval. Okay, the textbook also said that observation number 59 and observation number 60 are also the outliers, but I don't know. I think if you just draw the confidence intervals, these two observations might still be in the confidence interval, but certainly this observation number 58 is too way off. Okay, so by looking at this, it seems that we need to take care of this observation number 58 and possibly observation number 59 and observation number 60. Okay, but to do this like outliers stuff is actually it's not a very easy task. Okay, so there are a couple of ways that you can address the outliers. Yes, but they are not very easy to do. So the first is that you will consult the process engineers to gain more insights. Yeah, so you need to know like what is observation 58, what is observation 59, what is observation 60, what happens at that time. Okay, so you want to see if this is, they call it like, if this is an additive outlier, so which is the outlier that is just by recording errors, okay, or sometimes called like the measurement error. Or it is the innovation outlier, so that is, it has some impact on the dynamics of the process, okay? So that is this, there does have something happen here for these three observations, okay? And all these things actually affect the dynamics of the process. That might be also be the possibility. Okay, yeah, so I think like this, this first two solutions are, are definitely very good solutions, but it is very hard to do because you have to have a very good knowledge, or you have to have a very strong, like the background of this data very well. Okay, and otherwise I think to do this too is not that easy. Yeah, but I mean, that's the beauty of the research. So if you want to do the research and you do find those outliers, I think you need to go back to the real dynamics of the process and to check. Yeah, but there's also some other options, and I think this is the option that most people use. That is just to fit the model without the outliers and see if this new model can have some similar, can have some similar estimates as the old model. Okay, so I think that's the people usually do in their analysis, even though I think this solution is definitely not as good as these previous two solutions. Okay, so this is also what this textbook does. Okay, so it do 3 estimates. The first estimate is that it uses all the observations. So it uses observations from observation 1 to observations 226. Okay, and it estimates the AR1, the coefficient of this AR1 is 0.823, and also construct a confidence interval for these estimates. So it's from 0.7494 to 0.8984. Okay, and moreover, it also do 2 more estimation. The first estimation is that it uses the observations from 1 to 57. And the other estimation is that it uses observation from 61 to 226. Okay, so in these 2 observations, you can see that it throws away observation 58, 59, and 60. Okay, and for the first estimation, it finds that the estimates of this AR1 process is this number, 0.8669. And for the second estimation, the coefficient of the AR1 process is 0.8950. And it argues that because both of these numbers are within this, I think, 95% confidence interval, so that means our original estimate is a reliable estimate. Okay, so that's what this textbook does. Okay, I think it's a good way to study this, but it still has some problems. So for example, because the nice thing is that in this data, observation 58, 59, and 60 are all consecutive observations. Okay, so that means you can estimate 1 to 57, 61 to 226. However, if the outliers, so for example, are observation 1, observation 100, and observation 200, then what you're going to do? They are not 3 consecutive observations. Okay, so that means do you want to do the estimation like 7 times? Okay, and moreover, suppose that you have like 10 outliers and all those outliers are not close to each other, what you should do? Okay, yeah, so fits the model, what's the outliers? Again, there's like no systematic way to do that. Okay, you need to do that like case by case. Okay, so in this case, you can estimate like 1 to 57, estimate 61 to 226. But in other cases, especially in those cases that without this consecutive like outliers, you perhaps need to do another way. Okay, yeah, so I mean, yeah, the outliers are very important, but I mean, for this class, it is not required. So if you do find some outliers in your residues, I think the thing that I want you to do is to talk about it, okay, to discuss like what those observations are. Okay, so for example, if you are doing a GDP estimation, and suppose that you'll find like the observations in year 2008, 2009 are outliers, then you would say that that might be because of the financial crisis, and that caused that, okay? And if you can do this model, like refit the model without outliers, that would be perfect, okay? And if you do not want to do this, I think that's also fine, but just tell me that like what happens here and what you think might be the reason that caused those outliers. Okay, so that's outliers, and the textbook says that, okay, so because of this, so we think that we will still use this ARIMA 110 model, and because our original model, the estimates covered, like the 95% confidence interval covers like these 2 estimates, so we will still use like this full sample. And that's what it got. And we can rewrite this ARIMA model to this AR2 model just by reordering terms. And this is what we have. Okay. Yeah, and finally, this example do some forecasting. And all these forecastings are the forecasting that we have seen in early class. Okay, so all these theories, it also talks about, I think, this IMA case, IMA11 case, the weighted moving average case. So we also covered that. So everything here, we have already done that. Okay, so that's the example. So the example that is new to us is this outliers part. Okay. Okay, so any questions? All right, so if there's no questions, there's one more example. I think I don't want to do it here, but you are definitely, you can check it yourself. So this is an example number 2, so which is also in the chapter 4 slides of the BK, so you can take a look at this. Okay, so pretty much similar stuff. Okay, so now I think that's the ARIMA model, and now I want to move to the S-ARIMA model, the seasonality model. Okay, so which is again another very important topic for this class. Okay. So we will start with the seasonal model by, maybe first have some motivation of why we want to do this seasonal model. So for the models that we have discussed so far, the serial correlation or the serial dependence of the current observation to the previous observations was often strongest for the immediate past and followed a decaying pattern as we move further back in time. Okay, so because of this, we will do a AR1 or AR2 because the current observation is strongly correlated with its immediate past. Okay, but for some systems, this dependence shows a repeating cyclical behavior, and this is particularly true for the business and financial data. And this cyclical pattern sometimes is called the seasonal pattern. Okay, and can be very effective used to further improve the forecasting performance. Okay, and luckily the ARIMA model that we have discussed is very flexible, and it can allow us to include this seasonality pattern into the ARIMA model. Okay, and you can imagine like the S-ARIMA model, the S just stands for the seasonal. So it's a seasonal ARIMA model. Okay. So let's look at this example. This is an international airline passenger data from year 1949 to 1960. And this is a monthly data. So this is January, I think this is June and down to December. So it's a monthly data of the international airline passengers. Okay. So a couple of things that you can realize from this raw plot. Okay, so the first is that it definitely has an increasing pattern. So as time passes, the passenger that took the airline for international travel increases. Okay, so this is very easy to see. And the second thing that you can see that this data does not have it's not homozygosity, right? So the variance in 1949 is much smaller than the variance in 1960. Okay, and actually you can see there's an increasing variance. Okay, yeah, and more importantly is the seasonality pattern here. Okay, so you can see that in the early months of each year and also in the December and November and September, the people that's taking airline for international travel, the international airline passengers is smaller. The number of international airline passengers is smaller than the international airline passengers in the mid of the year. Okay, so you can see in June of each year, the international, you can see this peak in every mid months of each year. Okay, so this is very clear. Okay, and what causes this? It might be because that in summertime people like to travel, but in winter times people will stay home. So I don't know, but that might be one explanation. Okay. Yeah, and we can also like show this seasonality pattern and this increasing trend pattern by looking at the year and by looking at the month. Okay, so this right top figure plots the airline passengers by year. Okay, so this plots like every year stuff. Okay, it's the every year from January to December. So you can see that in all this, like in all this July and August, the number of passengers is much larger than the passengers in January and December. And this is true for all the years. Okay. Yeah, so this suggests a very clear seasonality pattern. Okay. And this bottom left plot shows this, like basically shows this the trend. Okay, so it plots the airline passengers by month. Okay, so every month from 1949 to 1960. Okay, so this is, I think, maybe, I don't know, months July or months August. Okay, and this is other months. But you can see that if we just focus on each month, we can see that it has a very clear increasing pattern. Okay, so this interaction plot suggests that there is some seasonality and there's some variance. Sorry, there's also a increasing trend. Okay. Yeah, I think that's what I just talked about. Okay. Yeah. So in order to study these patterns, we first want to do some data transformations. And as I discussed, we have a trend, we have the heteroscedasticity. So what we want to do is to use the difference techniques to address the trend and use the log transformation to address the heteroscedasticity. All right, so yeah, and this is, I think, what the textbook does. It does a log transformation. Yeah, so that's the plot after the log transformation. Okay, so you can see after we take the log transformations, the variance of the airline passengers becomes pretty homoscedasticity. So the variance in year 1949 is similar to the variance in year 1960. Yeah, even though it seems that the variance here is a little bit larger, but I think that's, for right now, that's totally acceptable. Okay. Okay, and it also like do like those interaction plots for the log transformation data. And you can still see that we have a increasing trend and we have like this seasonality pattern. Okay, so this again suggests that we will use some like first difference or maybe second difference to address this trend. And we will also include some seasonality patterns to address this seasonality observations. Okay, so I think that's just a introduction, and now I think I'd like to switch to the whiteboard to talk a little bit more about the theory of the seasonality data and how we can like study the seasonality data. Okay. So S ARIMA, and this S stands for seasonal. Okay. Okay. So some intuition that how we can build up this like seasonality in our time series, okay, in our model. So in the airline example, so in this airline example, you can see that the peak of the airline passenger is the mid of each year, right? So that suggests like this underlying seasonal lag is 12, right? If we are looking at a monthly data, right? Because for every 12 months, the number of passengers like goes to its peak, it becomes the largest. Okay, so this suggests that the underlying underlying seasonal lag is 12, and more importantly, if you use monthly data. So if you use quarterly data, then this lag is 4. Okay. Yeah, I will write it down. Okay. And moreover, if you use yearly data, then there's no seasonality. Okay, but that's not good because that means that you might I don't know, you might underestimate this model. Like your model cannot fully capture the full dynamics of the airline passengers, so which is not very good. Okay. So just remember that in the standard ARMA model, so the lag that we use is usually like 1 or 2. So for example, like in the AR1 model, we use just like the past observation as our explanatory variable to explain our current observation. So lag is usually very small and usually very close to the current observation. Here you can see that this lag becomes very large. Okay, it's like 4 or 12, and it actually does have meanings here, right? The meaning is that it is a seasonal lag, right? It is the lag that comes every 12 months or every 4 quarters. Okay, so okay, so this is a pure ARMA PQS model. Okay, so let me explain what each of these elements means. Okay, so this xt is standard, it's just your time series, it's your observation, and this wt is the white noise. Okay, so this is your observed time series. And this is the white noise. Okay. The important part or the difference part is this big phi PBS. Okay. So this is equal to 1 minus phi1 b to the s minus phi2 b to the 2s. Okay. So here, big phi1, big phi2, and big phi p are the coefficients. Okay, so this is exactly the same as the standard like standard AR models. So in standard AR models, we also have like those coefficients. Okay, and we use like those small phi to denote those coefficients. But here we use like this phi. Okay, and this B is the X shifter. Let me write it down here. So phi1, 2 are coefficients. B is back shifter. And S is the order of your seasonality. So for example, in the airline data case, it's like 12. And if you want to measure it in quarter, then it is equal to 4. All right. So for example, this phi p s can be 1 minus 0.5. Let's see. Let's write it. Let's give this as a number. 12. Let's also give this p a number. Minus 0.3 b to the 24. Okay. So if that is the case, then 12 xt equal to wt. So this is a AR212 model. This model becomes what? This model becomes xt minus 0.5 xt minus 12, right? Minus 0.3 xt minus 24 equal to wt. Okay. Yeah, so this is a AR, I don't know, this is an AR24 model, right? Yeah, this is an AR24 model with lag 12 and lag 24. And all other lags are equal to 0, right? So this is not like the way that, but you can think this is like very similar to like the standard AR model. So in the standard AR model, what we have is like xt minus 0.5, xt minus 1, minus 0.3, xt minus 2, right? This is like the standard AR2 model. Yeah, but here it is different. It is the AR2 with the season 12. Okay, so that means it happens every 12 months. So what you do here is t minus 12 and t minus 24. Okay, in that sense, you can capture like this seasonality pattern. Okay, and later I will talk about that actually like this AR212 model can actually be combined with this AR2 model. Okay, so you can have like this xt minus 0.5 xt minus 1 minus 0.3 xt minus 3 minus 0.5 xt minus 12 minus 0.3 xt minus 12. Okay, you can have this. This is just like AR2, I don't know, 212 model. Okay. Yeah, the nice thing of this model is that it both captures the seasonality and it also captures like this like immediate path effect. Yes, this is assuming there's no trend. We will later include like this I, this difference in the model. So right now we'll look at like the model with constant mean. Okay, so later we'll talk the difference, and we can also have the difference on the seasonality pattern. Okay, so later like the final model we'll build up is like a ReMA, say like 111 times 11112, something like that. Okay, so this is what we learned like previously, and this is like what we will learn for the rest of this class, or maybe not the rest, or not all the rest, but maybe 1 or 2 weeks. Okay. Yeah, very good question. Okay. Okay, so that's the example. Okay. Okay. Yeah, and moreover, I think this is not, people do not talk about that much, but you can check, actually, you can check if this model is a causal or an invertible, even though people do not check it that much. Yeah, to check this, the code, like the coefficient you have is like this actually. So that it's like the AR coefficients are actually, it's have like a 24 coefficients. Okay, so it's like 0, 0, 0. So you have 11, 1, 2, 3, 4. Yeah, you have 11 zeros and negative 0.5 and 0, 0. You have another 11 zeros, then negative 0.3. Okay, so that's your AR coefficient, and you put that AR coefficient into your R command, then do like this ARMA to AR. This definitely is AR. So you ARMA to MA, like your AR coefficient is equal to this. Okay, and your MA coefficient is equal to 0. Okay, then you do this and to check. Yeah, that's the thing that you want to check. You can of course check it's like causal invertible, but just remember here, like the coefficients for all the legs other than 12 and 24 are equal to 0. Okay, they actually exist, but they are just equal to 0. Okay, so you do not like put like -5, -3 into this. This is not correct. This just like checks an AR2 model, and here it's like this is the thing that you want to put in this AR2 to check. Okay. Yes, but this is just an aside. I think people do not check it that much. Okay. So once they have an estimate, I think they will just use that estimate to do the forecasting or to do some explanation. Okay, but you can definitely do such check. Okay, so that's the AR part of this seasonal model. And now let's Yeah, this is just an aside. Okay, now let's do the MA part. So the MA part is you can see it's just exactly the same as the AR part, right? So this is equal to 1 plus V1 BS plus plus B2 B2S plus B sorry, this is theta, sorry, theta Q B S. Okay. So an example. Let's say, for example, let's say do theta 2 B12. So that would equal to what? 1 plus give some number 0.5 B12 plus 0.3 B24. Okay, so then xt is equal to wt. This is wt plus 0.5 b wt minus 12 plus 0.3 wt minus 24. Okay, so that's a MA to 12 model. Okay, and also you can check, don't know, you can check the also and invertible of this model. Okay. Yeah, and finally, back to this big model, this ARMA PQS model we have is combining like this two parts together. This is a pure seasonality model. Okay, so this is a again, this seasonality depends on the frequency of your data. So if it's a monthly data, and if you are looking at like that airline example, the season is 12. And if you are doing a quarterly data, then it is 4. Okay. 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 Yeah. Final point, I think, for today's class is that we can combine this ARMA PQS with our ARIMA PDQ. to have a ARIMA PQ. Yeah, we haven't talked about like this big D, but you will later see that we can also do like this difference on the seasonality data. So that's the thing that I want to talk in the next class. Okay. So how we can combine it together and how we can determine from our ACF and PACF plot and how we can do those estimations and do the diagnostic checks and like all those stuff forecasting. That's what I want to do in the following classes. Okay, so today is just an introduction of like the seasonality data. Okay, I think I have a question here. No, yeah, you can ask me after class. Okay, so any more questions? Okay, so if there's no question, I think that is for today. And I also have a homework posted. It's due next Friday. It's all about like the ARIMA model, and it's like all empirical exercises. Okay, so if you have questions, please let me know. Okay, so that's it for today's class. Thank you.